Okay guys, in this video lesson we're going to take a look at specific heat capacity. Alright, now what is specific heat capacity? Well, when we define it, it's basically the capacity of a specific mass of a substance to absorb heat energy. Okay, so what that means for us is that every single substance in our world has a certain ability to absorb heat energy, and it relates back to how much it's going to change its temperature. Okay, we often get rid of the word capacity here. We just call it just what's the specific heat of that substance. Okay, because it is its capacity. So if you see the word specific heat, it means the same thing as specific heat capacity. Now, specific heat is very much like a density. Okay, if we take a look at aluminum has a very specific density to it, right? It's 2.69 grams per milliliter. That's its density. All aluminum acts that way. It's a relationship between the mass of the aluminum and the volume of aluminum. Now, for aluminum, its specific heat capacity is 900 joules per kilogram degrees Celsius. Okay, again, it's very specific to aluminum. It has its own capacity to absorb joules of energy with it. All right. So keeping that in mind, we can use specific heat to actually look at individual substances and actually determine what we're dealing with if we have an unknown substance. Right. So some things we need to keep in mind. First of all, specific heat is dependent on the type of substance we have. Okay, so aluminum will be different than brass. Brass will be different than copper, and so forth and so on and so on. Okay, it also is dependent on the state of matter. Okay, water's specific heat capacity as a liquid is 4,180 joules per kilogram degree Celsius. Okay, as an ice or frozen water, it's only 2,080. So it literally is half, which means if you put in the same amount of energy into liquid water and into ice will warm up twice as much. Okay, so you see there's a big difference there between those two things. All right. Now, looking at this, we want to do a couple of thought experiments. To do that, we want to take a look at these two bullet points. So first of all, a substance with higher specific heat requires more energy to raise its temperature. All right. So if I have two different substances, one has a specific heat of, let's say, 1,000, and one has a specific heat of 500. If I put the same amount of energy to them, I put them in the same oven, I put them under the same Bunsen burner, I put them in the same block of ice, whatever it happens to be, I change their energy the same amount. The one with more specific heat capacity is going to change temperature less, okay? Because it's the amount of energy it takes to make this happen, all right? So if I want them to have the same temperature change, I'm going to have to put more energy to raise it the same amount of temperature. Okay. Now, if we flip the scenario, if you have a substance with high specific heat, it can also transfer more heat energy into another thing. Okay. What that means is if you have something with high specific heat capacity, it contains more energy per degree Celsius than a counterpart that would have less specific heat capacity. Okay. Let me give you an example. If I were to warm up 2 blocks of metal, all right, and one of those blocks of metal, let's say it's 50 grams of it, is aluminum. Aluminum has a specific heat capacity of about 900 joules per gram degree Celsius. If I also warmed up, let's say, a block of lead, which its number is about 130, okay? So aluminum is, 6-7 times more than lead. If I had them at the exact same temperature, and I put both of them in my hands and held on to them, and they both came out of, let's say, boiling hot water. So they're 100 degrees Celsius, come out of boiling hot water. I put them both in my hands and I hold on. The lead one will sit in my hand and it'll feel warm, and my hand will absorb the energy that it has as it cools down, no problem. The aluminum one, I put it in my hand, it's going to burn me because it has so much energy inside of it that it's going to release as it cools down that my skin and my hand can't handle that much heat energy influx and actually can damage my skin. They start at the same temperature. The only difference between them was that the aluminum has a higher specific heat capacity. Okay. Now, that's also assuming they are the same mass, which we set up previously for that kind of thought experiment. All right. Now, looking at specific heat capacity, we have a label for that. It is joules per kilogram Kelvin or joules per kilogram degrees Celsius. The reason why it doesn't matter which one we use is because we're always tracking the change in temperature and not the absolute temperature. So the change in Celsius and the change in Kelvin are always the same thing anyway. It's the same number, so it doesn't really matter. Okay, here are some specific heat capacity values. So we take a look at aluminum, 897, brass, 376, methanol, 2,400, Water vapor. So as a gas, water is about 2,000. Water as a liquid is 4,180. Okay, so you see a pretty big range in there. Notice how our alcohols and our waters are much higher than metals. Okay, water has an abnormally high specific heat capacity, which is actually a good thing for us, because that means water has a really good ability to absorb heat energy without changing temperature very much. Okay, think about a repercussion of that. We have oceans that cover most of our planet. Okay, every single day we have sunlight that comes down and hits our oceans, hits our planet, and we absorb that energy. We absorb all this energy that comes from the sun. If we didn't have all the water on our planet to help absorb that energy and not change temperature very much, our planet would have much greater temperature fluctuations from daytime to nighttime. Okay? We see that in Minnesota because we're not next to a body of water. So our fluctuations in temperature changes more so than places that are closer to the oceans. Okay? Not only daily, but seasonally also. Okay? Now, at nighttime, water has absorbed all this extra energy. It now can dump that energy back into our atmosphere and the coastals, that kind of stuff, and the land around it. And it actually keeps the climate around the oceans much more temperate versus the extremes that we get here in Minnesota, right? So water actually is a very valuable that this number is high because it can absorb a lot of energy and it can release a lot of energy without changing temperature very much. Here's our equation for specific heat capacity. Now we use Q, and Q is the energy gained or lost. All right, so it really could be the same as just a delta E here, a change in energy that we've been using before. But in the world of thermodynamics, they use Q for this. Okay, we always have to deal with the temperature change. So it's going to be your final temperature minus your initial temperature. Okay, so maybe you want to write in final minus initial to remind us that's what it always is. And we of course have to deal with the mass, because the more mass we have, the change that's going to be. And finally, the actual specific heat capacity of it. Okay. Now, what this equation tells us is this: if we're looking for the energy change for a substance, okay, if we have, let's say we double the energy, okay, if we double the energy, that's going to create a change in temperature, okay, because we have a certain mass, we have a certain specific heat capacity on that. Now, if we look at it through the lens of how does it affect other things, if I change the temperature by 20 degrees, two different substances, okay, if you have a high specific heat capacity, okay, it's not going to change the energy. It's going to change the energy even more. If it has low specific heat capacity, it's going to change the energy less. Okay. Same deal with mass. If you have less mass, you have less changes in energy. If you have more mass, you have bigger changes in energy. So mass here plays a role also. Keep in mind also that this is a positive or a negative. So please use correct sign notation here, because when we gain energy, it's a positive change, and when we lose energy, it's a negative change. All right. So here's two practice problems for us to do. We have a bottom one here that is more conceptual. Okay, you have 20 kilograms of lead and 10 kilograms of zinc. What sample would take most energy to warm it up 22 kelvins? Okay. You could do math with this one, but you should be able to do that one just so you're thinking it through. This one you need to do the equation for. How much does the temperature of a 500 gram mass of silver change if it loses 10 kilojoules of internal energy? A couple of things to note. This is grams, this is kilograms, so you had to convert to kilograms. This is kilojoules, this is joules. If you're going to use these numbers, you need to convert this to joules. Okay? So pause the video now, solve these two, and then hit play again, and we'll show you the answers. Okay, so here's our first answer. So first thing I did here is I took my kilojoules and converted to joules, my grams converted to kilograms. I'm solving for what is the change, okay, in temperature. So I took my equation, rearranged it for temperature. I had my 10,000 joules divided by 0.5 kilograms times 235 joules per kilogram Kelvin. Put those two together, and I get 85.1 kelvins. Okay, so the change in temperature is 85.1. Okay, if I knew its starting temperature, let's say it started at 200 Kelvin, and it loses that energy, we would take 200 minus this to find our final in this case. Okay, so this question asks for the change. It could ask you for what's the new temperature also in this. The other one here, we have double the mass of lead, okay? But if we look at their specific heat capacities, lead's specific heat capacity is 130, and zinc's is 388. So zinc's is more than double that, because that would be 260. It's almost actually triple it, okay? So even though we have double the lead, we have triple the capacity for zinc, okay? So even with half the mass, it's still going to take more energy to warm up the zinc, okay? So you can kind of do a numbers comparison between those two things. All right, guys, so that is specific heat capacity. There's additional practice in your homework, and we also do more when we start applying this to the first law of thermodynamics in our next lesson. Thank you.